Hit the button, or this pad here, let's think about all of the forces that occur on the rockets. And then we're going to make a motion diagram or a free body diagram on the rocket. So if I hit this hard enough, it launches my rocket. And so there were a bunch of different forces that occurred during that process. So if my rocket launches this way, right, there's the part where it was experiencing the thrust from the air. So once the rocket launched, then let's talk about that. Okay, so while it was experiencing the launch, then there was the force of gravity, okay, and there was also the normal force, and then it experienced a force in this direction from the thrust, okay? And we want to be able to identify all of the forces that are occurring, so then we can calculate them, and we don't want to miss any forces. All right. So when the rocket was in the air, which forces were acting on the rockets? Yes. Yes. There's the force of drag this way. So we'll call that Fd. So I'm going to label this the force of drag, and just so I know what it is. So whenever you write your forces down, make a clear label so you know what it was. Right? What other forces are acting on it once it's in the air? Yes, gravity is acting on it. And so I'll write this Fg, the force of gravity. Does the force of gravity ever change while it's flying through the air? No, it doesn't change. All right, so we have the force of gravity, the force of drag, and any other forces? Well, none that we care about right now. So gravity and the force of drag, and yeah, and those ones are it, right? So the force of drag is really important for lots of different things. If a whale is swimming through the ocean, right, whales can move pretty quickly, but they have a pretty big cross section. And so as a whale swims through the water, it's constantly having to battle against the force of drag, which is slowing it down, and that takes energy. So the force of drag slows it down, which causes energy. And so whales swim from the North Pole all the way to the equator. And so we can calculate how much food do they have to eat to complete this process. Now, let's think about a whale. So here's a blue whale. And yeah, their flippers are this way. Okay, so here's my whale. I think yeah. Okay, so here's my blue whale. Oh, okay, he's a happy whale. All right, so when my whale is swimming in the water, what forces are acting on a whale while it's swimming? If it's going at a constant velocity. So V is constant. What forces are acting on my whale? Yes. Yes. There will definitely still be drag on the whale. So we'll have the force of drag. What other forces are acting on it? Yes. Yeah, the buoyant force. What does the buoyant force do? Yeah, it makes it float. So if an object is placed with a certain amount of water, then the water pushes back on it and things float. That's why metal boats are able to float, even though they're made out of water. So the giant oil tankers, they're huge, these massive metal objects, but yet they float because they displace more water than they actually weigh. And so it causes them to float. Some sea creatures are naturally buoyant and some are not. Sharks, for example, are not naturally buoyant, and so they tend to sink. Their buoyant force is not strong enough to actually keep them afloat. So if a shark ever stops swimming, it will sink. And so sharks never, sharks, at least some sharks, never stop swimming. So they're always swimming. Right, so we've got our buoyant force. What other forces do we have if the whale is swimming? Yes. Yeah. So there's a thrust, right? So it's tail. It swims with this tail. So there's a thrust force for the whale. Okay. What other forces act on it? Thrust is a good one. That's really important. The what? Yes. So we have the weight of the whale, mg, or we'll call it fg, the force due to gravity or its weight, which is a lot for a whale. I think a whale weighs as much as 23 elephants. So blue whales are the biggest creatures that ever lived. There's one more force that's also important since it's swimming. This one might not be so obvious, but there's also a lift force. So when it's swimming and water's moving over it, this one is called lift. And just like an airplane, the force of lift pushes up on it and keeps the whale from sinking. So we've also got the buoyant force, and then we've got a lift force that's pushing it up. Okay, so and that's really important for sharks because if a shark didn't have the lift force, it would sink. Okay? Now, if a blue whale is swimming at a constant velocity, so I think they can swim at maybe 30 miles per hour if they're in trouble. I don't know what the average velocity of a whale is, but if they're traveling at a constant velocity, what is the net force on the whale? We've got a lot of forces here. Yeah, it's zero. So the net force, when it's swimming at a constant velocity and the depth isn't changing, is equal to zero. So my net force is equal to zero if I'm swimming at a constant velocity. Okay? But if to keep it swimming at a constant velocity, that means you're always having to overcome the force of drag. Okay? So there's a constant force that's pulling you down, pulling you back. And so that's always going to be slowing the whale down. Okay? And maybe that's not a huge force, but it's not zero, and it's definitely a significant force for a whale. Okay? Now, we haven't talked about this yet, but we're going to. And if we want to think about energy, we're going to say force is equal, or force times distance is the work. And work is energy. Right? And so if you think about this, um, the whale has to provide this much energy for it to keep swimming over a long distance. So if we said, all right, the whale is going to swim from the North Pole to the equator, we have our distance here, and we also have the force of drag. And so we could calculate, which you will in a little while, we could calculate how much energy the whale is going to need to go from Antarctica to the equator. All right. Now, for a whale, okay, it's got to supply at least this much energy to keep moving. But is this all the energy that we need? What about if you're running? Okay, so if you're running, if I'm jogging like this, I'm chasing my son, I have to supply energy to overcome wind resistance, but to actually keep moving and get my muscles to move, that also takes energy as well. Okay, so we're also going to have energy from swimming. So this is for animals, this is a metabolic energy. This is the cost of energy that it takes to swim. So if the question is, all right, if it eats a ton of krill and it uses that energy to swim, how much of that energy do you think actually goes into propelling the whale, and how much of it is just lost from the act of swimming itself? Let's guess. What do you guys think? It might be similar to humans, right? If you go for a run, you're going to burn a lot of energy. Where does all the energy from the food go if you start running? How are ways that you lose energy? Yeah, you produce ATP, right, to get your muscles to move. And so some of that energy goes into actually moving your muscles. Where does the rest of the energy go? Yeah. Yes. You make a lot of, you lose a lot of energy to heat because your body is sort of an engine. And to keep an engine running, you have to expend energy, okay? And we're not going to do thermodynamics in this class, but I think you'll probably take a thermal class, or maybe do it in biology. But to keep an engine running, you have to expend energy. And no engine is 100% efficient. That wouldn't be possible. And so you lose a lot of energy just from heating up your muscles, getting them hot, having your muscles work. That all takes energy. Now, I don't know if whales sweat or not. Maybe they do. I guess it just gets washed away. I don't know if whales are sweaty or not. But they lose a lot of energy to just the act of swimming. Now, their tail is so big, okay, that if you were in a small boat underneath the whale and it slapped its tail down, it would crush you and the boat. So its tail probably weighs as much as an elephant. So it takes probably a lot of energy to keep the whale swimming. Okay, so for the case of our whale, we have identified their lift force, I think, is up like this. Okay, so our total forces in X and Y have to be balanced. If the whale stays at the same level in the water, it doesn't go up or down, and it swims at a constant velocity, then our net force is equal to 0, and so the forces have to be balanced. Okay, so that means the force of drag has to equal the force of thrust in order to keep it swimming at a constant velocity, and our buoyant force plus the force of lift have to equal the force due to gravity. Okay, so gravity is pulling our whale down. It's pretty massive, and all these forces are balanced. And And so for any physics problem you do, it's really important that you identify all of our forces. Okay? So think about what forces are present, and then make sure that all of those forces are balanced. All right. So we're gonna look at the problem of the whale in depth later. Probably when you start to feel sleepy in the second half and you guys start taking a nap. Then we'll do a problem to wake you back up. All right, so let's look at. Now you do have some homework that's due. So let's look at what the book has to offer. All right. I think I got most of the gadgets plugged in. All right, so there are other forces. There's of course the spring force. So if we compress something, and we will use the spring force. Your muscles are kind of like springs a little bit. When you supply an electrical signal into your muscles from your brain, so an electrical signal passes down through your body, it goes to your nerves. There's a chemical reaction. It tells your body to start producing ATP, and then your muscle moves your arm, but there's a component of spring force in your muscles. Okay, so you can calculate the spring force from your muscles. We're also going to deal with the force of tension. Okay, and I actually brought some string with me so we can measure the force of tension. Now, the force of tension that will cause the sled to accelerate, if you're at an angle like this, then you're going to lose some of that force. So if you are trying to make things accelerate quicker, you want to decrease that angle. So more of the force goes into accelerating your sled. Oh, wait.
You're not screen sharing.
Oh, thank you. So sorry. All right. So here's our sled. Okay. And we could think about our tension in the slide right here. And so we could say, all right, there's a triangle here. All right. Let's break down my components of forces. Okay. So my force of tension is the red arrow. And I have a component in the X direction. And that's the component that's going to make the sled accelerate. Okay. So if we knew the angle of our rope, then we could find the X component in the string there. And then we also have a Y component. That part is not going to help the sled accelerate at all. It's only the part of the component of tension in the direction of the plane. So that's what's going to make our slide speed up. Okay. All right, we've also got the force of friction, okay? And friction is interesting because one important characteristic about friction is that if you have, say, a tire or even a shoe, so you see a lot of sports cars with really big tires, and you're like, wow, that must have a lot of friction. But actually, it really doesn't depend on how big your tire is, because friction comes from a microscopic interaction on the atomic level. And so if you were to take an electron microscope and look at those surfaces, there's actually only very small amounts of area where they interact. And actually the force of friction doesn't depend on the area. It depends on the normal force. So how heavy something is. That's going to determine the force of friction. But it really comes from what's happening on the atomic level. Okay. Now, we also have the normal force. A normal force is always perpendicular to the surface. So whatever angle your surface is at, so if it's like this, so if I put my phone here, I put this thing on here, then the normal force is going to change as I change the angle. So my normal force will be changing, but it's always perpendicular to the surface. It always points at 90 degrees from the surface. Now with my little device here, when I get to a certain level, then the acceleration the force becomes big enough in this direction where it will overcome the force of static friction. So static friction is acting on here right now. And if I want to get this thing to move, I have to increase the angle until the force from gravity is big enough so that it starts to accelerate. So when I get right there, I go like this. Then about right here, that's my critical angle, where the force due to gravity starts to get big enough to overcome my frictional force. Right? And so if I wanted to find the force of friction of this thing on the sled, I'll turn this on. And then I'll plug this on in. All right, so here's my, get rid of force. All right, so I'll start my sensor. Okay, so I've got the green one, and it's at a little bit of an angle right now. So the green one is AZ, that's perpendicular to that. So if I set it flat here, then my other forces are 0. Okay, so there's only acceleration in the Z direction. Where's the acceleration from this coming from right now? Yes. Yeah, it's just measuring the force due to gravity, and then it's telling you what's its acceleration. Now, it can't move because it's sitting here, so the normal force is pushing against it, which makes this object solid. Now, when I lift this object up, okay, now when I get to an angle here, I'll use my napkin dispenser. Okay, so as I've increased my angle, X is not 0 anymore. So the blue one is still 0. If I increase it a little more, oh no, wait. Okay, so the blue one is becoming more negative now. Okay, and why is the green one positive? Isn't gravity negative? Well, it's just because if I turn this over, then it becomes negative. So it depends on which way I hold this thing, because it says, all right, if my force is going this way, then it's positive. Okay, so if I flip it over, then it's negative the other way. But the blue one, AY, so it says, all right, Y is going down this way, it's pointing this way, so it becomes more negative. So let's find our critical force. I don't know why it's doing that. So I'm gonna stop that. And I'm gonna turn this around. So I'll make it positive. Everything positive. We'll just say gravity positive for now. All right, I want to find what the force of friction is on here, and I can measure that like this. As I raise this up, okay, I'll get to a place where it'll start to slide. Okay. So I will stop it. And we'll go right into this region, and then I'll make this bigger. All right, so it looks like I'm gonna turn off the green one. Okay, so right where the blue one drops off, that's gonna be my force due to friction. Okay, so I can measure what the force of friction is by looking at this plot here. I'm gonna go right at the end. So right there, it looks like my acceleration got up to about 5.5. Let's do it. Let's go into analysis mode. I'll take my average value right there. And so it says up at the top, mu, my average value is 5.54 meters per second squared. Okay, so that's my that was my acceleration due to gravity. Okay, and I need to get its mass because no matter what is happening, you can always say that F is equal to mass times acceleration. And let me make sure, am I sharing my screen? Yes, I think I am. Okay, so let's measure my device here. I'm going to do it in grams, see how much this thing weighs. All right, it's 202 grams. Okay, so let's calculate my force. All right, so this is my static friction force. Well, at least I can measure. This is what my force sensor was reading right before it left. So I'm going to say this is the force that was acting. We have mass times acceleration. So I had a mass of, my mass was 0.202 it's grams. So that would be 0.202 kilograms. And my acceleration is 5.4. So this is meters per second squared. Okay. So now what force are we measuring here? Is this a force due to static friction, or what are we measuring with this sensor? Well, the sensor was telling us what the normal force is. right? So that's the force that this thing was experiencing, right, while it was sitting on here. If it's flat, then the normal force is m times g, but it wasn't flat, so that's going to tell us what the normal force is at an angle. All right, so I can calculate this. All right, so I'll say 0.202 times 5.45. So that's going to give me, for this force, it'll be 1.1 newtons. So 1.1 newtons is my force right before it started slipping. Okay. Now, for this part here, okay, we let's say we want to get our angle here. Okay, and what I did was I said, okay, here's my inclined plane at some angle, and I have a normal force for my plane. Okay, so it's like that, and I want to get my angle between here and there, and so I want to get this angle right there. How could I get that angle? Because what we calculated here was we calculated my normal force. Okay, so that was my normal force, and I know that mg is going this way. So this will be that is the force due to gravity, which is m times g. That's my normal force, or that's the force due to gravity. Okay, so if I say, all right, my sensor exerts an equal and opposite force on the block, then there's going to be a force like this, okay, right there. So that'll be negative. That's the negative of my normal force. So it'll be minus n. And now I've got a triangle. This, okay. So the 90-degree angle of my triangle is here, right there. The hypotenuse is m times g. The adjacent side of my angle. So remember that this angle, theta, these two angles are the same. So this angle is the same as that angle. So how can we calculate our angle? Yes. Yes. So you said, all right, could you say that one more time? So cosine of theta negative normal force mass times gravity. Yes, that is right. So, because we know what our normal force was, we got that from our sensor. So now we can get the angle, and we know what m times g is. So down here, I'll calculate m times g. I'll say the mass is 2.02 times 9.81. Okay, so that gives me, that's my normal force, right? And I'm gonna say, I'll say here, m times g equals this. So I'm gonna store that as a variable. So I say mg equals that. And then my normal force, I'll call this capital N because I think N is already taken by something. Okay, I'm gonna say, all right. I'll say capital N is equal to, we said 0.202 times 5.45. Okay, so 1.1. And now I can, up here, I'll say arc cosine of minus NN divided by mg. And then I want this in, I want it in degrees. So I'll multiply it times 180 divided by pi. And wait, where did it give me the answer? Okay, so my angle is 123. Does that make sense? What is 123? That's kind of funny. 123. Maybe I reverse my signs here. If I say that this is positive, actually, if I say, okay, this is negative, but also mg is negative. Okay, so that's a 56-degree angle. Does that seem reasonable? So AB, that doesn't seem right. That doesn't look like 56 because if it was 56, oh wait, no, I was holding it up like this, right? It wasn't sitting on this thing. Yeah, that makes sense. It was like about here. Okay, I believe that now. Okay, so we found the angle. It works, guys, because I was like, that doesn't look like it. But this, let's actually, we can test it. Okay, so get up here. Oh, maybe. Okay, that's maybe. Okay, I believe it. Because I always have to check it and say, okay, I know what the calculator is telling me. Like first it gave me 123 degrees, and I'm like, 123 degrees from what? So I guess if it was 123 degrees, it would start over here, and then it would go all the way up to here. So I needed to subtract it from 180. So, but if I subtract 123 from 180, then that's about, that's about 56. So that's about right. So this was 56 degrees on this side because I messed up my negative sign when I found the arc cosine. Okay, so that seems pretty reasonable, right? So we found a critical angle where this thing starts to slide. And then we could, if we wanted to, but we're not going to do it right now, we could find the coefficient of kinetic friction. All right, so I'm going to delete this, my little drawing right here. But this whole inclined plane business, we're going to use this a lot. So hopefully you are familiar with this. It'll also be on YouTube. Yeah, I'm recording this. Okay. I think I'm recording it. I think I'm sharing it. Yes. Okay. Yes, and it's recording. So you can go back and review it on YouTube, but this drawing, we're going to use this a lot. So, all right, I'm going to go back. All right. And I also put this presentation up on the Pearson website. So if you like to download it, it actually works now. I made sure it works. Right? I forgot to hit save. And so I uploaded it, but then I didn't hit save. So, okay. All right. So hopefully you can identify all of the forces. In the book, they talk about, okay, draw a circle around your object and then think about every object that goes into that surface, and that can be applying a force to your object. So when you're trying to figure out what your forces are, draw a circle around it and think about, all right, what objects are interacting with my skier here? Well, if he's going up the bunny hill, there's the force of tension that's pulling him up the hill. There's the force of friction. He's in contact with the ground. So friction is pulling him back. There's also the force of gravity, which is pulling him down the hill as well. Okay, so we would need to think about all of those forces. So identify your object of interest and draw it as a point particle. So just draw it as a dot. And then from that dot, okay, so first, of course, draw a dot. And then from your dot, think about all of the forces and just draw them out. So here's my tension. I've got the normal force acting on him. Gravity's going down this way. Friction's pulling him this way. So think about all of your forces and then and make sure you don't miss it. Okay. So locate every point on the boundary of this curve where the objects touch your object of interest. And hopefully, if you've got all the forces, then it shouldn't be too bad. Okay. Label each force clearly so you don't forget what it is. And then name and label each long-range force acting on your object. So gravity or the force of a magnet or whatever it is. Okay, so here's our common forces: drag, static friction, kinetic friction. What's the difference between a static frictional force and a kinetic frictional force? Yeah. Oh, sorry. Quiet. I'll call you guys. What is it? Wait, say that again. Yes. Yes, that's true. Now, in order to get an object to start moving, so which one is bigger, the static frictional force or the kinetic frictional force? Yes. The static is bigger. So once you start pushing on an object, you have to apply a lot of force before it starts to move. But once it starts moving, the force of kinetic friction is usually smaller. So to keep it moving, it doesn't take as much force, right? If you don't believe me, maybe you don't believe me. That's fine. I have a sensor here, so we can measure the force. All right, so I'm gonna turn on my force sensor. I think I'm sharing the whole screen. There we go. All right, so I'm gonna reset this. Turn it on. And then I'm gonna go down here to force. And here's my acceleration. Okay. So when I start running this, okay, the force on my sensor here is, well, it's 0 because I didn't calibrate it. But I'm gonna start pushing on it. And let's zoom in a little bit. And we need to make it a little bit better. We need to put some stuff on it. Okay. All right, this is better. Okay, so I'm going to start pushing on my force sensor here. What happened? So I'm going to start pushing on my force sensor. Stop it. Okay, so there's the kinetic friction. Okay, so I'm applying a force. So to get it to move, okay, here we go. One more time. To get it to move, I have to go here. Maybe let's zoom in more. So let's try it on a smoother surface. Once the move, well, it doesn't work right now, but the force of friction is real. All right, let's take a break, and then I'll figure out why it didn't work. All right, let's take a 10-minute break. So let's be back at 5 after 12. All right, well, let's go back to our sensor here. Okay, so I have added some weights to my sensor. And let me share this. Go. Okay. So I've added some weight here, and I'm going to start pushing on the force sensor a little bit. So this thing starts to move. And so as I keep applying force, all right. So let's zoom in on the data. Okay, so let's look at the motion of this thing as I started to apply force. So the first part here, the slope is where I'm increasing my force, and the force is getting bigger and bigger. And then when it finally slips, happens right about here. And as I keep pushing, then so the first part is the force of static friction up till right here. When I get to a certain point, the force from my hand overcomes the static friction, and then it starts to move. And after this point right here where it starts to move, the force due to kinetic friction is less slightly than the force due to static friction. And somebody asked, well, Dr. Wisby, why is that true? Why should static friction be different than kinetic friction? Well, the answer is maybe complicated. So let's start with an example using our rocket. So there is an ancient Greek philosopher, I think his name was Zeno. He came up with this thing called Zeno's paradox. At least I think it was Zeno. I don't remember his name, but I'm pretty sure. If I fire this rocket at the wall over there, it hits the wall eventually. But the problem is this. So, all right, let's take a vote. How many people think that this hit the wall? Raise your hand. Did it hit the wall? Just raise your hand. You can be honest. There's no shame. Let's double check our experiment. Let's see if it actually hits the wall. You tell me if it does or not. Okay. I'm firing the rocket. Did it hit the wall? Okay. Now let me ask you this: Did the rocket travel half the distance to the wall? Okay. So it got you about right here. Okay. And then did it travel half the distance to the wall from here? Okay. And did it travel half of this distance? Did it go half of this distance? What about, did it go half of this distance? Half of this distance? Did it go half of this distance? What about now it's going half of the distance? Does it ever not go half the distance to the wall? Because if I have 2 points, can't I always divide that distance in half? I don't know. Are your fingers touching? Are you sure? What are your fingers made out of? What are the atoms made out of? Electrons. How big is an electron? How teeny? It is mega teeny. In fact, it's so teeny we can't even measure a size. It's basically as far as we can tell a point. It has no radius whatsoever that we can measure. Scientists have tried. They've been trying for 70 or 80 years to measure the radius of an electron. How big is the radius of a proton? We can measure that. That's about, it's on the order of maybe a few, actually that's an atom. So, but it's really small. So it's less than an angstrom. So the protons are also very small. And so how close is the electron to the nucleus of the atom? It's pretty far. So the atom is made up of mostly empty space. So when you bring your fingers together, what actually touches there? Do the electrons ever actually hit each other, like bounce off of each other like pool balls? No, they don't. The electrons never actually touch each other. The protons never touch each other. They interact through a force at a distance, which is the electrostatic force. The electrons repel each other. So then when you touch your fingers together, do your fingers ever touch? Do atoms ever touch? Atoms never touch. So that rocket over there, it never hit the wall. You thought it hit the wall, but it didn't, because atoms never touch. So nothing ever touched. Right? So is there a desk here? Am I touching a desk? No, I'm not touching a desk. So how do I know that the desk is there? Is this even a desk? I mean, most of the atoms in this desk are like 90%, 99% empty space. What's the nucleus made out of in the atom? It's made of other smaller particles, right? Those are called quarks. How big are quarks? They're even smaller. And it's hard to measure a quark because they can't exist outside of a proton. We can get estimates of the upper limits of their radius. They're a little bit bigger than electrons. But even the proton is mostly empty space. So and when I look at this desk, is there a desk here or is it just empty space? So really there's no desk here. So I'm not actually standing in a classroom right now because this classroom is just empty space. Maybe you guys don't even exist. All I know is that I exist because I think, therefore I am, right? So all I can say for sure is that I might be real, I think. So when these particles are sliding across when these things are sliding across each other, this frictional force is coming from electrons that are interacting through the electrostatic force, and they're repelling each other. And so when something is not moving, there's kind of a stronger bond. So it could be like a van der Waals interaction. That's a type of electric bond. When you have two things that are close together, they can form these weak electrostatic bonds called van der Waals. It's a van der Waals interaction. It's not like a covalent bond. It's a lot weaker than that. And so when it starts moving, then you have to think, all right, these electrons then are sliding past each other. And basically it's complicated. But we can measure it, and so therefore it's real, right? We can measure it, it's real. So we measured it with this, and so we know that it's real. Because if I could do this experiment, I could say, yes, I can measure this. And I can say, look, I measured it. It must be real. People say, do masks work? I would say, well, if I put this on my phone and I sneeze on it, I'm like, ugh, and I pull this off, I can say, yes, this blocked most of my snot. Masks work. There, we proved it. So just if someone doesn't believe that masks work, just take their phone and sneeze on it. Get a bunch of snot on there and say, don't you wish you had a mask on your phone? That's how I know masks work. All right, so here is the force of static friction is greater than the force of kinetic friction. Okay, that's good to know. All right, so let's go on in our presentation. All right, so here's what we want to do. All right, we're going to work on a problem today. Let's define our problem. All right. So let's talk about blue whales. Okay. I like whales a lot. Whales are the biggest animal that ever lived. And so what I want you to do today is I want you to calculate how many tons of krill a blue whale has to eat to get from Antarctica to the equator. And you might say, Dr. Wisby, this is a physics class. Why are we talking about biology? Because biology is just really a subdivision of physics, right? So how do we do this? Well, let's go back to our model here. All right, we're going to say, and you're going to have to use the Google for some of this. Okay, so don't be afraid of the benevolent computer overlords. They're only here to help us. All right, so you're going to need to find what is the thrust from a whale's flipper. Okay, so we're going to have the thrust from the whale's flipper. Okay. And we're going to say that when they're swimming, the force of drag is equal to this thrust. Okay, so here's our force of drag, and here's our force due to the thrust. All right. And we also said the energy it takes to swim is equal to force times distance. Okay, so we're gonna make some assumptions here. We're just gonna say that we're gonna make an approximation. We're gonna say that the whale swims at a constant velocity when it's migrating from the South Pole to the equator, because there are whales that live. There's a group of whales that live in the North Pole, and there's some in the South Pole, and they migrate to the equator in opposite times of the year, so they don't actually ever meet each other. So let's calculate how much energy it takes to swim. So you'll have to find, all right, what's the distance if you swim along the circumference of the Earth? Okay, so you can look up the radius of the Earth. You can find the circumference from, and are we traveling around the entire Earth? How far around a circle would we be going? A quarter. So it will go from the South Pole up to the equator, right? So you can find that distance. Then we'll look up the thrust of that a whale has when it swims, okay? And we can calculate how much energy that would take. And then we also need to look up how much energy, how much metabolic energy does a whale use while it's swimming, just for the that it's going to use in all of its, for the act of swimming, right? So this is our, this is the work it would actually take. But then I guess if we need to, then we want to find, all right, how much energy does it take? So to get, so what we need is, we know that a whale is going to use so much energy, and a percentage of it can go into swimming. So let's find this energy, okay, just to do the work to swim, and then we'll multiply that by the total metabolic energy that the whale would need. So let's say that it could use 25% of the energy of its metabolic energy for thrust. Okay, so if this is the work it takes for just the whale to swim around, then we'll say, all right, there must be 70% more that it had to use to stay alive. So to move its muscles and to swim. And then we can find the total energy cost. Okay, and then you'll have to look up, all right, how many calories does a krill have? I don't know. It could be similar to a shrimp. So how many calories are in a shrimp? But maybe probably someone has figured it out for krill. All right. So the question is, how many tons of krill will the blue whale have to eat as it goes from Antarctica to the equator? All right. So find a partner. And let's see. Neil, would you be willing to work with Monica online? Is that okay? All right. So join the Zoom meeting. Monica, are you there?
Yeah, I am here.
All right. Neil is going to join the meeting, and you guys can work together. All right.
Okay.
All right. Do you need the Zoom link, Neil? Yeah. Yeah, it's always the same. All right. I'm going to put you guys in a breakout room. Actually, it doesn't matter. I'll just leave you like this, and then I will turn the volume down on my computer. Okay. All right.
Okay.
All right, Monica. So what are you guys gonna start doing?
I looked up the circumference of the Earth so we could take a fourth of that for the distance. But I can't really find the information about like the energy it takes the whale to swim.
Oh, okay. So we need to say, I think that's called metabolic energy. If you can't find it for scale, you might be able to find it for another mammal, and then we could use that.
Okay.
So let's see. Yeah, so Monica was saying what's the efficiency of a whale, right? So how much of its energy can it use for us, right? So if it eats, say, like 100,000 calories, how much of that energy goes into actually just swimming, right? So we want to look up I guess it's metabolic efficiency. Let's see, what does it say? So you're gonna have to do some research about this because I actually don't know what the answer is. But I know that if you have a car, right? So if you're driving your car, then a lot of the energy is you use for gasoline, or the energy from gasoline. Some of it goes into propelling your car, but about 80% of it just goes into heating up the car, and you lose it in friction and things like that. So animals are the same way. We're not 100% efficient. So when you eat a sandwich, some of that energy goes into just keeping you alive, keeping your muscles warm, pumping blood through your body. So some of that energy is, and a lot of it gets turned into food. So that's what we need to find. How much energy do you get from food that you can actually use for like swimming, something? Yes. Yes, but it has to supply a constant amount of thrust to overcome friction. So if it's not constantly swimming, the drag, well, it's not friction, it's drag. So the drag will cause the whale to come to a stop. So it has to supply enough force to keep it moving all the time. And so that's the amount of force that you're going to use to calculate how much energy. So even though the net force is zero, right, it still has to overcome drag. If it stops swimming, then it will, and then it will slow down. So then the net force won't. Uh-huh. That's not, yeah.
Okay, so
No.
I found that
Because we know that
whales burn 707. I'm just gonna use the chat.
swimming is going to be yeah. I think we will. They're yeah, they're open feeders. So that's what they do. All the Hey Monica, yes, I think that sounds reasonable for the circumference of the Earth. I don't remember off the top of my head, but oh, whales burn 1,900 calories per 8 miles. Okay. Hey Neil, can you put that website in the chat? Thanks. That's my son, Ben. So I guess you're finding that they have to eat a lot of krill to survive. So I guess the question is, well, how many krill did you calculate that they would need to eat to go the from the Antarctica to the equator? Like, what's the number? 400,000 tons. That's for one whale. So I guess how many individual krill is that? It's like, yeah. So 4 million, huh? You got 170 million krill? Okay. So it's in the range of well, it's a lot. So I guess the question is then, how many krill are there in the ocean? Because I mean, I don't know what the density of how many krill there are, but there must be a ton. Now, when we do these calculations, I think we're making a lot of assumptions, and so we're really simplifying how they swim and eat and things like that. But this tells us that they need a lot of food, and so this is interesting. So I guess we should check then later. Maybe we can find probably someone who's calculated how much krill a blue whale eats. So let's compare. Well, I guess next for your homework, compare that value. So take your calculation and compare it to, I guess, how much a blue whale eats in a year, because this can tell us a lot about how the blue whales live. Yes. So there's a guy here in the physics department that actually does research about this. He models a blue whale in his computer. They use this thing called CFD, and they calculate the coefficient of drag on a whale really precisely. And then he works with biologists to try and understand the whale better. And they put a sensor like this on a whale that can measure the whale's velocity, acceleration, and so they can see what happens while the whale is feeding and things like that. So, all right, well, that's it for today. So, give me your, well, I guess you don't have a copy of it. So, yeah, take a picture of your work on your phone and email it to me today. So send me a picture with your phone, take a picture, and then save your paper or whatever you're working on and compare it to how much the known value is that whales eat per year. So look up how much they actually eat. I'm sure people have calculated it, and compare your number to what the known value is. And if you are in the lab with me, you don't need to go downstairs. Just come upstairs and let's meet up there. Hey.
So they burn, I'm saying they burn 2,000 calories per 8 miles.
Okay.
Okay. This is how many miles they went. So,
yeah.
So they traveled this many miles to get to the South Pole to the equator. This is how many, per 8 miles they burn 2,000 calories. So just basically that, 4 million calories.
Oh, so this is, okay, so this is the number of calories
that they burn
to get from the
South Pole to the equator.
Okay, but then 2,000 calories. All right, so you need to figure out, where did you get the 2,000 calories from?
Per 8 miles. So I got it from up here. They burn 2,000 calories per 8 miles. So then in 16,000 miles, they burn 4 million calories. Then I did that divided by 2.4 calories per krill.
So I think you're okay. So you're close. So you're at 16,000 miles divided by
So this is basically a stoichiometry. So I knew that this was 16,000. This was 8. I didn't have this one. So I knew this one was 2,000 calories per 8 miles. So then
so you should actually multiply 2,000 calories by that.
yeah, and then I did that, and then I divided by 8. And I got that.
Okay, so you got 4 million calories. Okay, and how many calories are in a krill?
Krill 2.4.
Oh, okay. So they only need. Oh, okay. That seems reasonable. Okay. I don't know how true it is, but your logic seems reasonable. Okay.
And the best logic here, I just use the first the reading as this one,
Mhm.
and I use my arm to get the length of the circle, and I use the density function to calculate the look of that. Then it's because I assume the motion is constant speed, so it's just should be equal. And the drag should be equal to
Okay.
yeah. Then I just finish the graphs. And it's here is the density of the waters and the constant motion speed and the frictional stress and the area on the surface as well. So I get the FD, just the graphs. Then I just this here is the total work speed to do it to the wall.
Okay.
And then I just assume the trail is the weight of trail is 2 grams, and the energy is about 93% of the trail's weight. So that's basically yeah. So
Okay.
I just use the divide this and get the
Okay.
that's
All right. Thank you. Yeah, just go upstairs.
Thank you, like and subscribe down below.